Thank you, Dr. Kimmerai. My name is Matthew Tucker, and my presentation today is the efficacy and economics of precision soil sampling strategies for site-specific pH management in peanuts. So we're going to shift gears a little bit here. So a little background on the importance of pH for peanuts in particular, and all row crops in general is we like to have a range of about 6.0 to 6.5, and low pHs and high pHs can cause issues with plant health and can also create toxicity levels of certain nutrients, as you can see in this table here or in this chart. And lime applications in our area are used to increase our soil pH. And typically in our area, most all growers now are using variable rate applications, while some are still using straight rate applications, but a vast majority have moved to a variable rate application. And so with that, we have quite a significant amount of nutrient variability in our fields in South Georgia. And so the way to find that variability is with soil sampling. And so we can soil sample in multiple different ways: composite samples, grid samples, zone samples, and to be able to capture this spatial variability that we can then create a prescription map and spread based on the prescription map and aid in this nutrient management. And so I like to say that our prescription maps or our variable rate applications are only as good as our prescription maps, and those prescription maps are only as good as the method of soil sampling that you chose. And so the motivation for this research is that growers are interested in making data-driven decisions, but the big thing is that that data really needs to be quality data and needs to be cost-effective. And so the objectives of this study are to evaluate the efficacy of commonly used precision soil sampling strategies and to analyze the economics of these strategies. So this study was conducted in two fields, one in Worth County, about a 32-acre field, and one in Colquitt County, about a 93-acre field. And both of them have pH ranges from mid-4s to mid-6s. And so we have two different strategies that we looked at: our grid-based strategy and our zone-based strategy. So with our grid-based strategy, what we did was we created grids across each of these two fields on 1 acre, 2.5, 5, 7.5, and 10-acre grids. And we used the point sampling method. So we went to the center of the grid and we collected within about a 30 feet radius of that center, and we pulled on 6-inch depths, and we pulled 12 to 15 cores at every center. And this is represented a little bit better here on this slide, where you can see across this field. And yes, we actually pulled where every one of these points are. So we did not use our 1 acre grid to create a 2.5 or a 5 or whatever. So we actually created the map for each of the grid sizes, and we went and pulled this field 5 different times. And so what that, in all actuality, whenever we have the 2.5, the 5, the 7.5, and the 10 added together, we end up having soil samples. We nearly double the amount of soil samples that we had to begin with. And so what we end up with is 1 sample per every half acre in the field. So that comes into play here with the zone sampling. We created zones based on electrical conductivity and soil brightness index, which we got from Planet Imagery. And so what we were wanting to do with this is to separate the fields based on like areas of the field. So that being soil texture for electrical conductivity, or soil brightness, which would be soil color for the soil brightness. And so we created maps for both of the fields with both of these zone strategies. And what we did was overlay all of the soil points that were pulled. So that would be for the 1 acre all the way up to the 10-acre grid. And then we started removing points so the points would fall into the zones. And so then what we did to make and I know this gets to be a lot of information here, but what we started to do was continually remove points. So we have EC at 50%, where that, or soul brightness here at 50%, where 50% means 50% of the total amount of points that we collected in that field, which equates to about a 1 acre grid. But what we see is that those points are not in a 1 acre grid. They are more of a directed sampling method where we go to that, stay within the zone. So we hope to have the samples all be very similar within those zones. And so what we did was continually reduce the amount of samples, so then we could reduce the cost of the sampling itself. So the data analysis was done mostly with SMS Advanced, and that was the spatial analysis, and we interpolated all of the data there using the inverse distance weighting, IDW interpolation. Correlation analysis was conducted across all the sampling strategies with Jump Pro, with an alpha of 0.10 or 0.1, and all the prescription maps were made in SMS as well. So moving to the results, and this is the results for the grids here. So what we see on the left of the screen is correlation analysis for the grid sizes. So all of these grid sizes are correlated back to all of the soul points that we have for the field. So that is our true spatial variability, is what we're calling it. And so what we see for both fields, field 1 and 2, we have a very good correlation for the 1 acre grid. But as we decrease the amount of points by increasing our grid size, we start to reduce the amount of correlation we have. And when we started looking at this, we were thinking that this was, great information, but we started thinking this isn't spatial data. And so what I mean by that is, if we look in the 3 maps that we have here at the bottom, the first one is a line recommendation for the field using all of the soul points that we have. And then the second one is a prescription map with the 2.5 acre grid. And the third one is the difference between those 2 maps. And so this allows for the information for us to know spatially where we increased or decreased the amount of fertilizer, or lime in this case, that was supposed to be applied. And so in the table above those maps, we see for both fields where we had on target applications, over target applications, and under target applications. And so what we see here again is, as we increase the grid sizes, we decrease the amount of on target application, and this is the trend across both fields. And so now we move to the zones here. And again, I'm going to say EC 50, EC 25, 20, 15, 10, and 5, and for soil brightness the same, but that is the percent of all of the soil points that were used. And so what we see here is a very similar trend, that the more cores that we use, the more points that we use, the higher the correlation is to all of the soil points, or our true spatial variability. But the one thing that I want to point out here for both EC and soil brightness is EC5 essentially equates to a 10 acre grid, but we're pulling samples in directed points, or locations that we, instead of creating a square in the field, we have zones that we went and pulled from those zones, where we have a higher correlation for both EC and soil brightness for both of the fields with the EC5, which is again the same, essentially the same amount of points as a 10 acre grid, that we have a higher correlation here than we did for the 10 acre grid. And this translates again back over to the application accuracy that we see at the bottom, where we have our own target amounts. And we see across, in field 1, we see across all of the different sampling strategies, we have pretty close to 80% for most of the strategies, until we start getting like down to 2 and 3 points per field. While still at EC5 and soil brightness 5, we still have over 75%, which is a tremendous increase, or not a tremendous, but it is an increase from the grids at that same size. So I know this is extremely busy, but this is the economics for the zones, or for the grids, I'm sorry. And so what we're looking at here is the number of samples that were pulled for each field, the amount of lime that was called for that sampling method, and then the total amount per acre here in this column, as well as I added on the percent on target that we have. So for the grids, what we see, the trend that we see for the field 1 is that as our sampling points are decreasing, the amount of money that we're spending per acre is also decreasing, with the exception of the 2.5 acre grid. And what we also see is that our lime in tons is increasing. And so really the take-home message here with this is that although we do see a decrease in the amount of money that we're spending per acre, we can also look on the side or on the percentage on target and see that we are not applying the fertilizer in the correct places. And so what we're really seeing is that we're spending less money, yes, but that money could have been spent to have a better soil sampling strategy to be able to actually have better application accuracy. And so we'll move to the zones here. And what we see here is a very similar trend to the correlation and application accuracy. Here is that we still see, and you can see in the lime column in the tons, where the amount of application, or the amount of product that we're putting out, is very similar for all of the methods, and our percentage on target is pretty good for a vast majority. And so really the best thing to take home from this, and I'm sorry that I'm having to kind of rush through this, but the best thing for us to take home from this is that zone management, there is a good opportunity for zone management. And so really what we want to see is that, or what we have summarized here, is that the study suggests that as grid size increases, the correlation to the true nutrient variability, which is all the soil points, decreases, as well as the on-target application. Correlation values and application accuracy increase as the amount of soil sampling points increase. And for the economical aspect, depending on the amount of error that a grower is willing to take, and soil amendment accuracy, the study shows there's opportunity to decrease the number of soil samples, which would decrease the overall cost, while maintaining over 80% accuracy. And so what we want to work on later this year and continue on into next year is the more work on the data collection of zone delineation, and really working on using multiple spatial data layers to be able to create zones to really better our management practices. So with that, I thank you, and I thank the Peanut Commission and UGA Extension. And with that, if we have any time for questions.